Hi everyone, good evening. Welcome to Café Sci on the 1st of November 2021. My name is Brad Peroni and we are going to get started with our talk tonight with Sandra DeVincent Wolf from Carnegie Mellon University. Before I introduce Sandra, I'd like to take a moment, of course, to thank our sponsors. Café Sci is presented by PPG and sponsored by Cook Mayo Site. And of course, we couldn't have Café Sci without the wonderful support from our Café Sci audience. We love interacting with you here on Zoom, and we do look forward to moving Café Sci back on site very soon. Please stay informed by visiting the Science Center's webpage or following us on our social media channels to get the announcement when Café Sci is back on site. And I would also be remiss if I didn't remind you that there will be questions and answers with Sandra at the end of the talk. So please, as we are going, feel free to put all of your questions in the Q&A box at the bottom of your Zoom window right down there. We'll take those questions at the end, so feel free to pop those questions in as they come up. But let me tell you about our guest tonight. Sandra DeVincent Wolf has 15 years of research, development, and engineering management experience in advanced materials and manufacturing, working in national laboratories, a startup manufacturing company, and large corporations. Her technical work experience is followed by over 10 years in executive management of nonprofits, where she was responsible for leading initiatives from conception through implementation and assessment, internal and external communications, strategic planning and operational implementation, program management, corporate and government relations, education and outreach, and staff and volunteer engagement and development. If that sounds like Sandra has been a very busy person, then you are correct. She joined the College of Engineering at Carnegie Mellon University in 2015, and she is Senior Director of Research Partnerships and is responsible for facilitating research partnerships and the growth of new initiatives, centers and institutes, and industrial consortia across the College of Engineering, especially as they apply to materials and manufacturing. Sandra is also the Executive Director of the CMU Next Manufacturing Center for Additive Manufacturing Research and Education, where she leads the activities and partnerships of the center and its consortium. She's additionally the Executive Director of the CMU Manufacturing Futures Institute, where she works to identify, connect, leverage, and accelerate research and manufacturing across campus to support innovation that will accelerate the path of discovery to commercialization to increase U.S. competitiveness and drive economic development in the Pittsburgh region. And it is my distinct personal and professional privilege to turn things over to Sandra to get started with her talk, and I look forward to all of your questions in the Q&A box down below. Sandra, I'm going to turn off my video, and the floor is yours, and possibly also Fern's.
Thanks, Brad. Thanks so much, and welcome everyone. Thanks for joining me tonight. I'm going to be talking a little bit about metal 3D printing, and what this is really going to be is an introduction to what those of us in the industry call metal additive manufacturing. So what is additive manufacturing? I'm hoping a lot of you are familiar with 3D printing, at least with maybe plastic desktop 3D printing. Maybe you've seen this in your libraries, in community centers, maybe in your schools. Maybe you have a plastic 3D printer at home. There are a lot of history behind this. It's actually been around since the 80s. And metal 3D printing works much like plastic 3D printing, just on a different scale, different types of materials, and different conditions. But the steps, the major steps, are basically the same. You start with a computer-aided design model or a CAD model, and you can build those in almost any type of CAD program. There are some very common ones that are used in the universities and in industry listed here. You take that 3D model and you slice it into layers, and there's software that helps you do that. And then you deposit a material one layer at a time, generally starting from the bottom, and then going up one layer at a time. And there's different types of processes that do this. And as I mentioned, this really started back in the 80s with a process called stereolithography. And that uses a laser to trace a shape on a liquid polymer that then cures it using photolight and then turns it into a solid. We're going to focus here on metal additive manufacturing and metal 3D printing because I think that is less familiar to most people. And so additive manufacturing, or AM, really breaks down into a number of processes. So you have your polymer or plastic-based processes that I just mentioned. And then there are two different types of metal processes. There is a group of processes called indirect metal processes, and then some that are direct metal processes. And I'll focus on introducing you to both of these today. Also, I want to note that there's 3D bioprinting that's going on, and there's a tremendous amount of work that's being done in the 3D printing of soft and biological materials to make implants and even repair hearts. So why all the interest in additive manufacturing or 3D printing? Well, really, even though this has been around since the 80s, there were a couple of developments about 12 years ago that really generated a lot of interest in the population and in industry in this. So the first was maker machines, or these sort of desktop 3D printers that came about for polymers or plastics hit the market. So you had MakerBots, you had machines made by Cube Pro and Form One. These were very high resolution polymer machines, and they cost some about $2,500, some about $1,000 and less. Today, you can get a desktop 3D printer, plastic 3D printer for use at home for under $500, even just a few $100s. And as you've probably seen, they're popping up in a lot of middle schools and high schools, libraries, and community centers. Around the same time, automated metal 3D printers came online. And so there were two different processes that were introduced at this time. One is called a laser powder bed process, and the other is an electron beam powder bed process. And I'll talk about both of these as we go on. But both of them use a metal in a powder form. It's much like cinnamon or flour is in its consistency of tiny metal particles. And you use either a laser or an electron beam as the energy source to basically bind your particles together as you're trying to print one layer at a time. And I've got some videos to show you each of these processes. And this was really the first time that the industry demonstrated that you could make a generic 3D shape automatically out of real engineering alloys. So it wasn't just out of plastics, it was out of titanium and aluminum and steel and nickel alloys and other types of alloys that are out there in great use today. And as I mentioned, 3D bioprinting is a really interesting and fast-growing area as well. So let's talk first about indirect metal additive manufacturing. So these were the first practical attempts to make metal parts. And basically what happens here is you print with a powder and you use a binder. So instead of using a heat source to make these metal powders melt and stick to each other, they use a binder that's kind of like a glue that then you put in the oven and you solidify the whole thing. And then it has to go into another process, into a furnace, to really, really sinter, they call it sintering, the part to get the particles to really stick to each other, to partially melt and stick to each other so that you have a solid part. Now, this process was introduced actually by a local company, the X1 company, which is in North Huntington, PA. It's actually one of our partners. And so these approaches are pretty well established. There's a lot of research that's happening right now in this area. It's an inexpensive form of metal 3D printing, and it has a lot of attention right now. On the next slide, I'm going to show you a video of our binder jetting machine that we have in our lab, and I'll explain a little bit about how it works. So this is one of our students, Luke, in our lab. So what you can see is what we call a build box, and it actually has powder in it. I've got my annotate key here. Here we go. And so in this area, this is a bed of metal powder. So this is stainless steel powder that's just sitting here waiting to have a process done. So what's happening now is that plate had dropped down, and now we need to fill that area with powder. So this is coming across. It's got a light that's preheating the bed a little bit. It's dropping a pile of powder in this area. And when it goes back, it's going to use a roller to spread that powder out nicely so that we have a very smooth, even layer. So you can see the roller right here at the edge, the black roller that's rotating. And this, now we have a perfectly flat powder bed. Over on the left side, this is the printhead. So this type of process actually works very much like an inkjet printer that you would have at home. And so it comes out, and you see the head is going back and forth, and it's dropping binder particles or glue droplets basically in the shape of a circle. And they're going to do many of them at once. So this was a part that we were building, the bottom of which is a disc. And so it's going to go through this multiple times. It's going to drop down. It's going to spread another layer of powder. The binder is going to come out. It's going to drop in. And it's going to continue going until it builds everything that was in the original drawing and programmed into the machine. This is a fairly inexpensive process and also very easy to use. So next type of metal additive processes are direct metal processes. And these are processes where there aren't a lot of intermediate steps, where you just directly print the shape. And when you take it out, it's basically done. You don't have to consolidate it with more material. You don't have to put it in the furnace for another process to get to basically your finished part. And so with this process, you can make all kinds of very complicated structures. You can print designs that you couldn't possibly machine out of traditional machining steps. There are some limitations, though. While there's a lot of design freedom, and as I said, you can 3D print, as you can see the little sphere of a lattice that we have here, that would be impossible to machine or to just make out of a chunk of metal in the machine shop. The drawbacks, few drawbacks to this are that parts can take a long time to build. This is a pretty slow process. And if you want to build a lot of parts, or if you want to build a large part, it can take a day, it can take many days, it can take a week. Now, building small parts like these images that I have shown here that are about 1 inch in diameter, building a series of those, you can do probably in about 10 or 11 hours. But building, say, a 5-inch tall part that's maybe 8 by 9 inches, that could take you like 5 days to build. We also have sort of a limited amount of materials that can be used in these processes right now. This is an area of research that is very, very active so that we can get beyond just the traditional aluminum, steel, and titanium powder alloys that are out there now. They're also a little bit expensive, so this is something that you have to factor in when you look at whether or not you want to use the process. But what's really exciting is that you can build a shape automatically with fixed machine settings. So of the direct metal processes, there are a few different kinds. And so these use what we call a metal feedstock, which is the starter material. And so there are some processes that can use wires, like a welding type of wire as a starter material, and many, many others that use powders, as you saw in the other video. And so I'll show you these different types of processes, and each one is best for different types of parts and different types of reasons. So this first one is called a powder stream process. As you can see from these nozzles, it's actually streaming powder particles. So it's like shooting them like almost like an aerosol, streaming them down. There's also gases in there that help protect the powder so it doesn't oxidize along the way, and also making sure that it's directed to where it needs to go. This is the first direct metal 3D printing process that was developed, and it's typically used for repair. So it's very easy with a process like this to start with a part that is broken, that is missing a chunk of metal from it, and to fixture it in the machine and allow a process like this to add material back where you might have lost some in a failure. And so I have a video here that I'm going to show you. This is going to briefly open in my other screen, and then I'm going to bring it over. So you can see with this process that it goes pretty fast, and you can lay down a good bit of material at once. So this is a part that had been chipped on its edge, and now you have these nozzles spraying powder, adding material to an area that needs to be repaired. Now, often at the end of this process, you have to go back and machine it so that you have the final dimensions that you want, so it's as smooth as you might want. But it's very simple with a process like this to repair parts and to add material where you may have lost some, or to even build up material from scratch. And here you can see it's making a process that's actually pretty thin. And this would be finished machine down to something smooth at the end. Alrighty. This process is fairly similar, but it uses a wire. So what this really is a really large scale welding process. So it uses an electron beam to melt the wire and a moving table. And you can build really, really large parts, as you can see here in the pictures. You can build something the size of an airplane wing. You can go to like 19 feet in length with this. This process has been around for a long time, probably 20 years. It's the fastest process as far as building up material goes. Of all of them, it's not particularly automated. It requires a lot of planning, a lot of computer programming, and planning on the machine. But it is really, really good for very large parts. There are times in certain industries, especially in the aerospace industry, where a company would normally use a very large forging or a cast part. And these days it can take anywhere from 6 to 18 months sometimes to get the material that you need in that size. And you could actually use this process to create that material, the big blank basically that you would need to then machine. As you can see, you can lay down material in a way that brings it close to what we call near net shape, close to the shape, the finished shape that you want, and then you can just machine it after that. So I'll show you how this works.
Talking about metal 3D printing, but who's delivering? Siaki is. With our patented EBAM metal 3D printers, we have the largest installed base of industrial metal 3D printers in the world, with more metal deposited on critical applications than anyone else. Only EBAM has approved parts in 4 dimensions: land, sea, air, and space, utilized by the world's most advanced manufacturers like Lockheed Martin, Airbus, NASA, Hitachi, and others. And we're building more machines and laying down more metal every day. EBAM is proven to reduce lead times, material cost, and waste up to 80% or more. For more information, talk to the Metal 3D experts at Siaki today and get EBAM working for you.
Okay, great. All right. Now, the next process is actually one of the most popular ones used out in industry. And this is an area where we at Carnegie Mellon do a tremendous amount of our research as well. And so this is called a laser powder bed process. So this is basically uses a powder bed like you saw earlier in the process from X1, the binder jetting process. But instead of using a glue or a binder, it uses a laser beam to trace out basically the drawing of your part that you've already pre-programmed and almost melt the powder particles that are hit by the laser together to basically bind them together and form the first layer of your part. This is currently the most successful of all the metal additive processes. It's used for smaller parts. It's been used in automotive applications. GM just had a car release that has some parts in it. There are a number of examples of these parts in service. They're even being used in critical parts in the aerospace industry right now. You can use almost any available engineering alloy that you can get in powder form. That includes titanium, aluminum, stainless steel, tool steels, other types of carbon steels, nickel-based superalloys that are used in very high temperature applications. It's a little bit slow, and it does require heat treat, so some time in the furnace afterwards. But the surface finish on these parts is fantastic, and the types of detail you can get in these parts, as you can see in some of these pictures here, is really great. So this is actually from our machine on campus, and this is going to print out our center logo. So you can see the laser going, it almost goes like in stripes. So it's rastering, they call it, back and forth as it goes up and down in a path that's already been planned prior to this process. So that's a recoater blade, and it's spreading another layer of powder over the area that was just done, and now the second layer is going. You can see now it's going at a diagonal. So this process naturally rotates the beginning of each layer so that it doesn't start in the same place it did before. And that evens out the heat distribution and some of the stresses that can build up in this part. Again, the bed drops down a little bit. Another layer is spread. And now the third layer that's programmed to go is running. You can see the laser rastering back and forth. And this is it running around and doing the edges. And again, it drops down. Now another layer is being spread. And the laser is coming to do the fourth layer, again, rotated somewhat from the last one. And this is exactly what it sounds like. So this is literally just taken from a GoPro that's inside the machine. And that continues on for however many layers your part might be. So for something small like this, where we're just building up some lettering on a plate, maybe you do 20 layers, maybe it'd be like 1/8 of an inch tall. For building parts that are a couple inches tall, you're gonna get, 500, 1,000 layers. For a part that's like 5 inches tall, you're gonna be looking at 5,000, 6,000 layers of a part. The other fairly popular powder bed process is called an electron beam process. There's a company called Arcam that manufactures, has developed this process and manufactures the equipment for it. Arcam is now owned by General Electric, but is still the process has remained intact. And so the only difference, really, one of the biggest differences here between the last process, the laser powder bed process, and this one, the electron beam powder bed process, is just the heat source or the energy source. So this uses an electron beam instead of a laser. This process was actually developed, and we have some of this equipment. It was made probably around 2004, 2005 timeframe. And it was made primarily for printing titanium alloys and for use in medical implants. So this is the process of choice for hip implants, knee implants, other types of bone implants, where rough surfaces are good so that bone ingrowth can happen easily. This process produces, you can see in the photos, a fairly rough surface compared to the others, and that's on purpose. So this is a very automated process. Again, it's made primarily for titanium alloys, and these are their alloys that are biocompatible and most often used in medical implants. And I'll show you a quick video of this.
If you work on a desk, this is a secret that no one's telling you about. I want to introduce you to my friend, the Loom Cube.
So this is actually in our machine as well. This is a little bit hard to follow because right now it's preheating the bed, And what you see, the crazy mess there, is actually one electron beam scattering around so fast that it just looks like things flying everywhere. And so you can see it's building out a layer of a set. This was a set of test samples for us, the cross section of which was a bunch of discs and then a bar. And so those were going to be material test samples that we would use. And so this process runs very much like the laser process. Sorry. Okay, so those are the main metal additive processes. Let's look at why somebody would even use this process in the first place. So there are lots of different things you can do with metal 3D printing. One is build prototypes. And so you can use this for presentation models. If you're designing a new part and you have to show it to a customer or your sponsor, you can build functional prototypes. You can use them as visual aids. You can do fit and assembly models. So you can 3D print different components in your system and test fit them before you go into production. You can 3D print tooling components. So there are a lot of times when a machine shop or a manufacturing plant or a manufacturer will need tools or molds in order to make parts, or just some sort of fixture or jig to attach things so that you can then machine them to attach a component that needs to have another process done to it. And having tooling made by a tool and die company can have long lead times and can take quite a while. So if you can make your own tools and molds and fixtures and things in-house, this can save you a tremendous amount of time. You can also customize them to fit exactly the kind of component you want to hold or you want to work on. And of course, you can use them for parts. And so the point here is to say it's not just for parts. So you can use them for prototyping to help with your design process, use them in tooling to help with your in-house processes, or actually print parts for sale for retail use and for other customers. These are especially good processes for things that are low volume and high value. For processes and parts that need to be customized, because it's very easy to design in customization. You can print really complex geometries and things that are impossible to make otherwise. So these are reasons to consider metal 3D printing in lieu of traditional manufacturing process. So there are a lot of opportunities when you 3D print something. So rather than just 3D printing the part as it is today, so say you have a part and you need more of them, rather than just 3D printing it, because oftentimes if you take a part that's made by traditional manufacturing processes and you just simply 3D printing it without changing anything, you're probably not going to save any money. So what you really want to do is get more out of it. And so you can design it for performance. So you can look at simplifying the design, or you can reduce the weight of it, because with 3D printing, you only have to put material where you really need it. You're not starting with a big chunky block and then ending up with extra material because you didn't machine it away. You're instead creating something almost from nothing. And so you can just put material where you need it. So this naturally ends up with things being lighter weight. Iterative design. And by this, I mean, you can design and redesign over and over again. And you can do this very quickly if you have 3D printing capability. So you can go through the design process, you can design a component or a part, and then you can give it a try. You don't have to send out an order, you don't have to go into production with it. And you can just keep improving on the design very quickly, because going to 3D print something may only take you a day or a couple of days, whereas placing an order for something in order to get a test part may take you weeks or months. You can customize these parts. So say, let's take a medical example. So you're getting a knee implant or a hip implant. You can actually take your MRI and turn that right into a computer-aided design model that then becomes your 3D printing model. And so now your hip joint or your knee replacement is customized to fit exactly you. And it's not hard to then do the same thing for the next person, so that not everybody has to have the same one. You can do very complex geometries. Here's an interesting reason to consider additive manufacturing, an opportunity that a lot of people don't consider. And this is something called consolidation of parts. And so this is when you look at a system rather than just an individual part. So maybe you look at an engine and it's made up of a lot of different parts, or you look at some sort of fixture that's made up of half a dozen parts. And instead of looking at the individual parts, you look at the whole system and look at redesigning and possibly printing that whole system as one part, or maybe just a few parts. And so then what you reduce is your number of failure points. And that's because you don't have so many parts that have to be joined together, either by welding or bolting or some sort of fastening. And the fastening points and joints tend to be areas where things break and fail in general. And so if you can reduce the number of failure points in a system, then chances are it's going to have an improved or longer life. And you can also shorten your supply chain. And by that, I mean, if you have a system that is made up of 10 parts, and now you can 3D print it as one, now you just have one supplier that you need to go to get that, rather than maybe a few different suppliers that you get all those different parts from, some of which you may have to wait on longer than others, or someone goes out of business and now all of a sudden you can't make your system anymore. So you can shorten your supply chain by consolidating how things are printed. And of course, you can decrease your time to market. And sometimes this is reason enough in industry. Even if it costs more, it's reason enough if you can be first to market with something and basically win market share, because you can use 3D printing to get things done quicker. Even though the process itself may take a while, getting that first part introduced to market can go much faster. And also you reduce material waste, because in the end, you're really only using the material you need rather than machining away material that you don't need. And finally, reducing inventory health. And so by this, I mean holding on to a lot of spare parts. And so this is true of many manufacturers. It is true for our armed services, for the Navy, the Army, just about anyone who produces parts have to have a lot of spares on hand, especially for parts that fail often. And if you could just 3D print them when you needed them, you would not have to hold so much inventory. And so here are some examples of different successes of using metal 3D printing. The first I mentioned earlier is design complexity. And so here are some examples of different types of very complex designs that are made with 3D printing. Now, some of these could be made with traditional manufacturing processes. You see the photo in the upper left. Obviously, that could be machined, but it's much easier to do via 3D printing. The pictures in the middle that have the lattice structures, those simply cannot be machined and are best done with a 3D printing process. We've got filters, we've got some medical implants. 3D printing is also very popular in decorative applications and in jewelry. So you can see some customized designs that are here. And off on the right, this is tooling. So you've got some drill bits basically that are made by 3D printing. And those, if you can see on the top tip of each of those, there's a little tiny hole there. These actually have cooling channels in them where cooling lubricants and fluids can flow through them so that the tools last a lot longer. And those are things that you simply cannot produce by traditional machining processes. I mentioned lightweighting as an opportunity for metal 3D printing. And these are areas where basically you put material where you need it and don't put it where you don't. And so, for example, lower left, this is an engine bracket. The original bracket is the one that's closest to the corner. And you can see that's a fairly bulky bracket that gets bolted onto an airplane engine and stays on it for the life of that engine. And then the two holes there are used to lift that during maintenance. But a redesign for additive, trying to optimize that design for 3D printing, you can see in the different versions of it that the ultimate design is very organic looking, but it has a lot less material to it. And this has been designed to be able to carry the same load, last just as long, And in the end, it actually saved money because it put less weight on the engine and less weight on the plane, which ultimately saves in fuel. And so not only do you have less material waste, you have fuel savings. And so in the end, this ends up a better design. And then you have different, like the photo in the middle, you can see the lattice structure, sort of the webbing netting type of structure that's called a lattice that is put into the sides of this bracket, basically to lightweight it. So that used to be solid. And instead of using a solid wall, you can design in a lattice that is just as stiff and strong as the solid wall was, but uses much less material. So your part in the end is much lighter. And so the other area of opportunity for additive that I mentioned was consolidation of parts. And this actually is one of my favorite reasons to use additive manufacturing. So as I mentioned, you got to think in terms of systems and not just parts. And there's have a lot of opportunities here, and I have a handful of examples of where this has been successful. So the poster child for consolidation of parts is the General Electric fuel nozzle. So you may have seen this in the news some years ago. So they had basically, the challenge here is they were designing a new fuel efficient jet engine. And this design had a very complex interior. It had geometry that was much too complex to manufacture. And it consisted of over 20 parts that needed to be welded or brazed, which is very similar to a welding process, in order to basically join those 20 parts into what would be the finished fuel nozzle. Basically, when they got done with this design, they found that it couldn't be made. And they purchased a number of castings and tried to manufacture these parts and join them, and they were not successful at all. So the opportunity here is to use a 3D printer for the part rather than just the prototype or the rapid iteration or redesign of their part, which they had been doing at the time. But instead, now we're going to look at actually 3D printing the part and not just 3D printing the prototypes. And so they used a laser powder bed machine for this. And the first build took only a few days to produce, and it was successful. And this is after, I don't remember if it was months or years of actually failing and trying to make this design any other way. And so here's the final part. The solution was manufactured successfully. They managed to consolidate what was originally made out of 20 parts into this one, which is now just 3D printed as a single part. It is 25% lighter. It is 5 times stronger. And they've improved the fuel efficiency over the previous design by 15%. And they had a much quicker design process. So you can see they've had a fantastic amount of success moving to 3D printing with this design. Here's another example from GE. So this is a very large turboprop engine. And so the challenge or the opportunity here is that this was a brand new design. It was something that they had not made before. And so their solution was to look at this after the success of the fuel nozzle. They were considering 3D printing and looking at consolidation of parts, and they managed to consolidate 855 components down to just 12, reduce the weight by 5%, improve the fuel burn by 20%, increase the power by 10%, cut the prototyping development time by a third, and reduce their test schedule from 12 months to 6. So this is another fantastic example of using 3D printing to consolidate parts and end up with all of this enhanced performance and lead time, cutting down your lead time as well. So here's a different type of example in the automotive industry. So GM and Autodesk partnered just a couple of years ago on their seat bracket. So this is the bracket that sits down by the side of your seat when you get in the car, where it fastens basically your seatbelt to the car seat itself. And so they had been looking at small upgrades, trying to make tangible improvements in this bracket so that it wouldn't fail or come apart during use. And so the opportunity here was in generative design. And by this, I mean trying to automate. So having an engineer work with a computer and some artificial intelligence in order to generate designs that basically optimize the part strictly for its performance. Not so much for its looks, but looking at for its performance, if you need strength in a certain place, if you need stiffness in a certain place, if you need it to be flexible anywhere, to basically generate a series of design options that you could then evaluate and recommend a solution. So this is a way you can go about spitting out a number of design options quickly. And so they were to have the opportunity to look at 150 designs. They were able to functionally optimize this seat bracket, consolidate what used to be made out of 8 parts into just one, and the end product is 45% lighter and 20% stronger. And so this was one of the first successes actually in the automotive industry of a metal 3D printed part going into service. This is one of my favorite examples because it's just so amazing. So this is a RF antenna, a radio frequency antenna. This is a very large system. This is the size of a very large backpack and it's very heavy. And so like out in the field, like someone in the Army, for example, would carry this around in a backpack around with them so that then they could communicate. And so the challenge here was to increase mobility and the performance of this antenna. The opportunity is to replace this process that included multiple stages, including brazing, which again is like a welding process, plunge EDM, which is a special type of machining process, 8 months of development. It took 3 to 6 months to build. So what they wanted to do was redesign this very large, heavy, multi-part assembly. So they combined some design, some simulation work, some mechanical engineering efforts and software programs used to optimize this design to focus on 3D printing or additive manufacturing. And the result, in my opinion, was amazing. So they consolidated something that was 100 parts down to 1. So this is printed as is, as shown, finished part. Reduce the weight by 95%. So now what used to be carried around in a backpack, a huge backpack, now can be literally held in your hand. Reduce the lead time from 11 months down to 2. And the cost, the production cost, was reduced by 20 to 25%. And they're non-recurring, meaning upfront, one-time only kind of design costs reduced by 75%. This is much, much smaller, and it has as good or better performance than the original part. So just finally, what's next for metal 3D printing now that it's out and there are lots of companies working in making machines and lots of companies, just about every company that works in metal manufacturing is looking at using it. There are a lot of us out there, particularly in the universities, that have some very active areas of research that are helping to advance this field. And so some of the areas we're working in include material development. So this industry really started with just a handful, maybe 7 to 10 typical engineering alloys that were used. There's a lot of research being done in developing new materials, whether it's adding certain elements or changing the chemistry of existing materials to make them stronger or more corrosion resistant or more biocompatible, to using completely new materials. There's a lot of what's called process monitoring and process development going on. So this picture in the bottom center, there you can see that's in our laser powder bed system. And you can see on the right-hand side of that picture, there are some hardware mounted in there. So that's actually an acoustic monitor and a camera. And so we do a lot of process monitoring. So we use cameras, we use pyrometers that accurately measure temperature. We have acoustic monitors that record sound, changes in sound in the system. And we use that information basically to determine what's going on in the process. And we're able to detect flaws, either visually or from temperature or even from the acoustics that we've now learned to recognize that allow us then to change the process. So there are a lot of things you can change when you're 3D printing. You can change the power, you can change the speed, you can change the diameter of the beam, you can change how much it gets hot in there before you print. You can put stall times in there between layers if you need things to cool off. There are a lot of different things you can do to improve the process. And so almost everyone who works in 3D printing research now is active in process monitoring and process development. Post-process development. So most of these parts, they end up cleaned when you're done. Some of them need to be finished machined, some of them need to go in a furnace. There are different types of post processes, meaning after the process, that can be done. And there's a good bit of research that's being done in this area. Incorporation of automation and robotics. So we're looking at trying to automate different parts of this process. This can be a bit time consuming to set up and to clean up. And so looking at using robotic capability to automate some of that. Also applying artificial intelligence or AI, and especially computer vision and machine learning to additive manufacturing. So this is a very visual and very data intensive process. So there's a tremendous amount of data that you can collect, whether it's in images or sounds or temperatures, or just sort of the build file that logs all the data of every single point, time and temperature and speed and power going on in there. And frankly, it's too much data to process for an individual. And so we've been making a tremendous amount of use of computer vision and machine learning to process all of the data that we get from our builds in order to better understand what's happening and to define parameters so that you can set your machine and be fairly certain that you will have a part that will print successfully and be defect free. And then finally, one of the newest areas of active research in metal additive manufacturing is large scale additive. So these powder bed processes especially have been fairly limited since they've come online, so to speak, these last 10 years. And building a part that's maybe a foot tall has pretty much been the limit for a while. And now they're looking, there are machines coming online and other types of processes that are going to allow much larger scale manufacture of parts. And just one last thing to show you a little bit of a snapshot of what an example of how we use computer vision and machine learning for reconstruction of data. So this part on the lower right that I have here, you can see the top half of it came out very well, the bottom half of it, not so much. And so we actually have a software package, basically, that one of our students had led the development of, that takes the images that are taken of every single layer of the part as it's being built and uses artificial intelligence and machine learning to analyze what it sees there and identify different types of problems in that powder spreading process. So when you saw in the laser powder bed process, you saw the recoater braid spread a layer of powder. It's very important that that layer come out really well, that it doesn't have, empty spots in it, that it doesn't have debris, it doesn't have, that the blade doesn't hop and cause streaking. There's all different kinds of problems that can happen in the powder spreading process that then lead to problems in your part. And this is an example of using that data to then make a 3D reconstruction of what was happening during the build, which you can see lines up very well to what we ended up seeing in the end. And this is a type of sort of quality control inspection process that you can use even after the fact to look at a part that you think came out great, just to see if there was something that happened or something that happened in the powder spreading process that typically leads to a problem happening on the inside that you can't see from the outside. So this is just one example of applying computer vision and machine learning to metal 3D printing in order to advance not only the process itself, but people's adoption and use of the process so they feel more comfortable about what it is they're getting when they can't see inside of it. And so in closing comments, there are a tremendous amount of opportunities for metal 3D printing, design flexibility and complexity, consolidation of parts, decreasing your time to market. Metal 3D printing can be used for all different types of things, including prototypes, tooling, and parts and components themselves. And as we tell people when we meet with them, to teach them about this and to work with them on research projects, is that it takes training, it takes partnerships, and you should just jump in and get started. And so with that, I'd be really happy to entertain some discussion and take some questions, Brad, if we have any.
We do have some, excuse me there. We do have some wonderful questions, some thoughtful questions already. And just as a reminder for anyone, if you didn't catch the very beginning of the talk, there is a Q&A function. It's usually in the bottom of your Zoom window. So feel free to put any questions that you have for Sandra in that box, and we will get to as many of them as we can. So I'm just going in the order these questions were submitted. Charles kicked it off with a couple of questions very early on in the talk. And the first question is, can you recommend a good open source CAD package for this purpose? And I assume this purpose, we can broadly say is some additive manufacturing.
So definitely. And so I had a few. Do you still see my screen? Do you see that slide, Brad?
Yep.
Okay. So well, these are very common ones used out in industry. And if by any chance any of you are students, you can get your hands on these packages for next to nothing. I know a student license for SolidWorks is only $25 a year because I have a lot of students that get it. But open source and free to download, I would try. So one of the simplest ones you could look at would be Blender. That's fairly popular, and that's a free download. Inventor, I think, does AutoCAD make that? I think can also be used. Most students I know when they're first transitioning into this will play with Blender. I would say it's one of the easiest to get to learn. Some of these other ones are a little bit harder to self-teach, but I would try Blender and maybe Inventor.
Excellent. And I would imagine that some of the other ones probably have some specialty features that you might discover that you need once you get a hang of the more basic software.
Yeah, and you could, but I mean, you can even use a very basic CAD software package for stuff like this. A lot of these have other things with them that you don't necessarily need for this. And also, once you pull your model into your printer software, what happens from there varies a little bit. So if you're just moving into a plastic 3D printer, you're pretty much almost set to go. Some of the metal 3D printers are that simple also. Others require the equipment manufacturer's onboard software as an intermediate step.
Okay. Charles also wants to know if there are facilities in Pittsburgh that will sell you time on these machines.
So that is a great question. So we have, I will tell you that we do allow sort of outside projects in our lab and on our equipment. Now it requires obviously our engagement and use of our technicians and those of us who know how to run these machines. But we do have internal and external rates for that reason. That said, a university will not print parts for you that you will then turn around and sell straight up at retail. Universities do not do work for hire, but we most certainly like to work with people to help prototype and test out designs, to do samples, things like that. As far as other metal 3D printing vendors, so there are service bureaus, actually, that you can go straight to, and they will be less picky about what they work with. We have even, so X1, the company that I mentioned, that's in North Huntington, so they're one of our partners. They actually do 3D printing for shapeways. So some of you in the audience, if you've ever played around online looking at 3D printing, there's a website where you can go and you can even find our pre-existing designs and stuff also if you don't want to design things yourselves. And you can literally order them through Shapeways. And there are different service bureaus or 3D printing houses, if you will, including X1, that will print on demand by orders. So it's like custom ordering something from Etsy or from, from, Snapfish or, any of these other, where things where you design what you want, you put in the order, and then it gets sort of farmed out to where there's capability, and then it gets done. And I can tell you from visiting X1, for example, that if you go there around the holidays, about half of their business is 3D printing for Christmas gifts that have been ordered through Shapeways.
So it's not just, industrial use making,
No,
nozzles for GM.
it's little models. It's little
Yeah.
wine bottle holders with your college logo on them. It's all kinds of stuff.
Fascinating. It just leads, gives people another creative tool to use to bring their ideas into physical space.
And if you want, if I could add one more comment, just to go along with that, if you wanted to play with this a little bit and not dive into yet into metal or just spend the money on producing a part in metal, even UPS, you can order 3D printed plastic parts from.
Oh, wow.
Yes. Yep.
So we have a couple more questions here. One, very simple and straightforward. The other, multifaceted. We'll go with the simple one first. How are the metal powders made?
Okay, so that's a good question. So there are different types of processes that you can use to make metal powders. I think I'm going to stop sharing my screen, and I'll pop it back up again if we need to get back to it. So there are processes mainly called atomization. And so metal powders have been being made for hundreds of years, right, to support the powder metal industry. So powder metal industry is responsible for production of mostly very large scale parts, where you have to put material into a mold and melt it or subject it to really, really high pressures to produce a part. And so to produce a metal powder, they take basically metal feedstock material, melt it, and blast it with a gas. So in what they call gas atomization, they use a gas, they blast the heck out of it to basically obliterate it into tiny little spherical powders. And these are tiny, tiny powders. So they are on the scale of, say, 10 microns to maybe 200 microns, with the average that's used in metal 3D printing being between like 15 and 50 microns. This is really small. There's different types of atomization processes. So you can use gas for that. You can use water for that. There's also a plasma atomization process. But interestingly enough, the majority of the metal powders made in the country are made right here in the Pittsburgh region. So within about 2 hours of here, we probably got 90% of the country's metal powder manufacturing. So companies like Carpenter, Ametek, ATI, which was Allegheny Technologies, Hoganas, Praxair, trying to think of our suppliers. There's a number of them, but where this is a hotbed for that here in Western PA.
Not only just a domestic thing, but a hyper domestic, very highly regional specialty that we have here.
Mm-hmm.
That's, yeah, I would have never guessed. This is so far out of my typical sphere that I would never know we had all those companies in the metal powder industry.
Yeah, we do. Well, the home really metals manufacturing is mostly born here in Pittsburgh.
Sure.
Between U.S. Steel, Allegheny Technologies, and Alcoa. And that's also part of why metal 3D printing, why we are a center for the U.S. in metal 3D printing here in Southwestern PA. And it's mainly because this area was born in the metals industry in the first place, right? So not only do we have a lot of capability associated with it, we have a lot of the sort of ancillary processes around it, like the heat treating and the machining and other kinds of things that go with it are here. We have the powder manufacturers, and then we have the workforce that's accustomed to working with metals.
Excellent. And you just answered Kitty Mama's question with how did we get this capacity for manufacturing metal powder here in the Pittsburgh area. So
Yeah, there's a long history
yeah,
of metals manufacturing of all different kinds. But the metals additive manufacturing, this being the hotbed, comes from a lot of that. And a lot of the research at a lot of the universities, it's not just us. So we have one of the leading research centers in this area, and we also have educational programs. We now have a minor in additive manufacturing and a master's program in additive manufacturing available to all of our students in engineering. But also University of Pittsburgh has a lot of, we collaborate with them on a lot of research. Robert Morris plays in this field a little bit. Penn State has a tremendous amount of additive manufacturing work and research and education available as well.
excellent. So I promised that we did have a multifaceted question coming up.
Okay.
And so I'll read off the whole question, and then we'll break it down into its constituent parts. When these production processes are streamlined, how much money does industry save on average? How many manufacturing jobs are or will be lost? And will these displaced skilled workers be retrained to work in AM? So let's take that first part there. So as much as you can, estimate, how much money can, an industry save in this streamlining of processes?
So I can't give a dollar value on that, but I can say it's in percentages. It can be very, very large. So going back to one of the first examples, that engine bracket that General Electric had. And so that actually took a while before it was a savings, and you had to factor in the whole system and everything associated with it, including the fuel savings for that. And so there was, I'm not sure what the percentage was on that one. I do know that, so General Motors just recently they're one of our partners as well. They were visiting recently for a media event around the launch of their new Cadillac. I'm not going to remember the name of it. I should have looked it up before this. Blackwing. Is it the race? It's a racing Cadillac, right? It's 600 some odd horse, 6 point something liter engine. It has 3 3D printed parts in it. And what they saved a tremendous amount of time and money on was the design iteration. So they went through the design process for that car. So that whole car, I took them 4 years to design or 4 years to produce, from initial concept to on the road. And that's not that long of a time for a performance vehicle of something like that. And their greatest achievement in that, aside from the amazing engineering that went into every part of that car, was the time cut down by using 3D printing as in their design process. So they were able to do iterative design very quickly, 3D print, test, go back to the drawing board, make changes, and just constantly doing that and turning around things really, really quickly. Think of a couple other examples. Then there are parts, things that you just can't make any other way. So if you look at tool bits, for example, that have active cooling channels in them, you can't manufacture those any other way. But your tool bit might last 10 times longer because you can actively cool it. So it doesn't overheat, doesn't break, doesn't chip, things like that. So, if that lasts 10 times longer, then there's your savings, calculation right there.
So it sounds like
and I'm sorry, that's not those aren't direct financial numbers,
but it depends on the industry and how they can be creative in applying the technology.
Mm-hmm.
But I think also probably a lot could be saved too whenever the costs for AM come down and processes get even quicker. That
right.
Can compound the savings too.
Yeah, and those are things we're working to do. We're working to come up with new materials. There are companies. Oh, so one of the other powder manufacturers, and I don't remember if I mentioned them in the beginning, in the area is Ametek. So Ametek is in the region, and they have a process that's different, a little bit different than the atomization process. And while I won't explain it, it results in powders that are very different, and they're choppy. in comparison. So they're not spherical like your traditional metal powders. They're very, it's almost like broken glass. They're very sharp, very angular and whatnot. But it costs very little money in comparison to produce those powders than it does the atomized powders. And so we've been working with them actually for many years on proving that those types of powders can be used in these processes. Because when metal additive manufacturing first had all this interest, one of the biggest costs was the powder and the powder itself. And the opportunity to reduce the cost of the material is huge. And so we've been able to prove that you can use those powders, which are very different and you would think would have a difficult time spreading, successfully 3D print with them. And that's a tremendous cost savings there as well. So I remember the last question is about the workforce.
Yeah. So how could this impact the skilled workforce?
Mm-hmm. So that's a really great question because initially, so there are a lot of people out in the industry, machinists, people who work in metal joining, welding, things like this, in the metal fabrication industries. A number of them originally thought metal 3D printing, if this really happens, maybe could take away my job. The same way, a lot of people worry about automation and robotics taking away assembly type jobs and other types of jobs like that. What I will tell you, so I have a technician who helps me run our metal 3D printing lab, and he has 35 years in the tool and die industry. He is a machinist, and he's been working with us for 4 years. And he actually goes out and does like outreach talks like these. And he told me that when he first heard about metal 3D printing, he and all of his friends and colleagues from work and what, they all thought, oh no, this will be the end of it. We're going to be out of a job. What he's come to realize himself from being a machinist working in the metal 3D printing industry is that there's always a place for machining. It's never going away. These other processes are still needed. And frankly, he'll be the first one to tell you he's a better machinist now for having worked in this industry, because actually machining metal 3D printed parts is harder than machining parts out of traditionally cast and forged material. Things that are produced by metal 3D printing tend to be harder as metals. And so it requires a different type of technique and requires a lot more knowledge about the metal and what can happen under certain conditions. And so I don't see this at all as a problem. It's actually an opportunity for you to expand your capabilities, expand your knowledge into yet another area. So metal 3D printing isn't going to replace manufacturing. It's disrupting it somewhat. It's basically another tool in the toolbox. It's not for everything. There are some things that you should continue to stamp, continue to press, continue to machine. If it's not complicated, probably you shouldn't 3D print it. If it's a flat fastener or bracket or a bunch of bolts, you should not be metal 3D printing these things. But as someone who works to support this industry as a machinist or a technician or an engineer, it just opens up opportunity because it can't totally replace it. The same is true of robotics and automation. So there's opportunities to sort of upskill, right? To broaden your experience and broaden your knowledge and apply it yet to something really interesting.
Excellent. So we have 2 questions left in the queue here. The
Okay.
next one is from Kitty Mama. When I was in grad school over 20 years ago, I used sputter coating to prep samples for EM. The first video you showed with the nozzles reminded me of my old sputter coater. Just a bit of nostalgia. So,
well, I'm sorry to hear that. So when I was in grad school, my background's in material science and engineering also. And while I did not have the pleasure of prepping samples for a TEM, I have plenty of friends that did. And remember them accidentally losing them because they're tiny, tiny, tiny little samples. And that's a challenging process.
Excellent. And we have one last question. And barring any other last minute questions that come in, I want to thank everyone for all the thoughtful questions and discussion that we have tonight. This question is, many medical implants or joint replacements contain ceramics. Can we 3D print ceramics yet?
Yes. Yeah. Yeah, I failed to mention that earlier because this was really just focused on metal 3D printing. So that is an active area of research. So we do 3D print alumina, silica, tungsten carbide, a number of different very hard, like high temperature materials. One of the processes that's best for that is the binder jetting process that was developed by X1 here in the region. That process in particular can 3D print almost any material. Because it doesn't use an energy source, you don't have to worry about how the material is going to interact with the laser or the electron beam because it uses this binder or this glue. So basically, if you can get it in powder form and get it to spread, you can use it in that process. And so we've had good success 3D printing ceramic type parts in that. I'm not 100% sure if there must be ceramic parts out in industry, and I'm sure X1 has produced some. And I'm sorry, I don't have a good example of one right now.
Well, don't apologize. Like you said, we were talking about metal tonight, so that's quite all right. If there are any last remarks from you, Sandra, people should, have a way to contact you or learn more about what's going on, this is a great time to share that.
Sure. If anyone would like to reach out, I'm happy to answer questions. Or if you happen to work in an industry that's really interested in learning about more and learning about what we're doing, you can just look me up on Carnegie Mellon's website. My bio is out there, and my contact information is published in numerous places on the website associated with the College of Engineering and the institutes and centers that I work with. Also, just say if you're interested in 3D printing and you've never taken too much of a look at it, there are lots of tremendous videos out there. Again, if you are looking to have something printed as a gift or a novelty, there are, Shapeways is one of them. There are sites out there where you can literally just upload a design or pick one and get it printed. Even in metal, you can have things plated, coated. You want a gold coated wine stopper, bottle stopper, you can get one. Lots of really neat stuff going on out there. If you're interested in learning more, there are a lot of different videos out there. There are for formal or sort of informal education. There are a lot of certificate programs. There are a lot of online courses. And then, of course, some of the universities have formal education in this space as well.
Excellent. Dr. Sandra DeVincent Wolf, thank you so much for being here with us tonight, and we look forward to seeing everyone here next month when we host Patrick Sherry talking about endangered species and the intersection of law and biology. Until then, have a great one, everybody. Take care.
Thank you.